In this recording, we're going to talk about how do you derive the demand functions from the given utility function. This is also one of the topic of an Indian Economic Services exam, indifference curve analysis and utility. That's the name of the topic. And there are certain kind of questions which have been regularly appearing in this particular topic. So what I've done is that I've taken up some questions from the past year papers, and this is also useful for people who are appearing for IAS economics optional. You have to know certain things. There are no ifs and buts about it. A little bit of maths is definitely required when you are doing an economics paper, right? So let's just do this. So the question was asked in 2009 paper. So it was question number 2. It says that show how demand function may be derived from a Cobb-Douglas utility function, right? Now, what do we have here? So we have a Cobb-Douglas utility function like this, u equals to xy, which is a Cobb-Douglas utility function. And my maximization problem is that I maximize my utility function subject to the constraint, right? My constraint is p1x plus p2y equals to m. And I set up the Lagrange. So Lagrange is one of the optimization techniques. We will talk about Lagrange in some other recording in detail, right? Right now, I'm just giving you a tool, right? So you just have to understand this, that you'll have to put up the objective function. This is my objective function, this guy. This is my objective function, and this is the constraint, right? There can be any number of constraints, and you just have to maximize your objective function or minimize your objective function subject to the constraint. So the technique says, of course, one very basic thing which you should understand is that it can only be used for differentiable functions, right? Functions should not have a kink, right? And the other thing which you also have to remember is that Lagrange is used for equality constraint problem, right? Lagrange is used for equality constraint problem. This is one thing which you will have to remember. So we are not solving for the inequality constraint problem, because that theorem is also like Lagrangian. I don't think so. I mean, they'll be asked in the IES paper, but still we may do one or two questions based on that as well. So what do you do? That you find out one partial derivative for each variable. So there are two variables here. One is x and another is y, and one for the constraint, right? So del L by del X, del L by del Y, del L by del lambda. Of course, I'm assuming that you have an idea how to find out the partial derivatives. So del L by del X is Y minus lambda P1 equals to 0. Del L by del Y is X minus lambda P2 equals to 0. And del L by del lambda is M minus P1X minus P2Y equals to 0. So you can just divide first by second. And this set of equations are called the first order conditions, right? FOCs, or first order conditions. So what you do is that you divide first by second, and what you get is basically y by x equals to p1 by p2. So my y is equal to x p1 by p2, and I can substitute this y equals to x p1 by p2 back into the third equation to get this m minus p1x minus p2. In place of y, I'll write this x p1 by p2 equals to 0, and I'll be getting m minus 2p1x equals to 0. So from here I'll get my optimal x star, which is m by 2p1. So as you guys could see, this x star is the function of m, p1 and p2. So this is my demand function, and I can substitute this x star back into the y here. So my y was what? X into p1 by p2. In place of x, I can write m by 2p1 into p1 by p2. So this thing becomes m upon 2p2. This is what I will have as my demand functions. So this was the question which was asked in the IES paper. I'm going a little further, right? And trying to assimilate one more question into this. See, the demand function which you have just found out, these are called uncompensated demand function, right? Uncompensated demand functions. But and these uncompensated demand function, I'm sorry, I'm putting the screen up and down many times. I'm so sorry. Uncompensated demand functions, these are the function of income and prices. Right? While finding out uncompensated demand function, the only thing which is varying is prices. And this nominal income is being kept constant. It is given to you. It doesn't change. Right? Then for compensated demand curve, that is for the compensated demand curve, what do you have to do? You only take the substitution effect into account and you ignore the income effect. in in the uncompensated demand function, you are taking care of the total effect, and in total effect you have both substitution effect as well as income effect. I will have a different recording based on this. So right now I'm just giving you the mathematical exposition of this, a very simple one. So for compensated demand function, only substitution effect is taken into account and income effect of the price change is ignored. And what do we do here? The compensated demand function is the function of prices and utility. This thing, please make this thing very clear in your head. Uncompensated demand function is the function of income and prices. In uncompensated demand function, income is being kept constant, and in compensated demand function, utility is being kept constant. These compensated demand functions, they are also called Hicksian demand functions. Right? These are also called Hicksian demand functions. Right? Okay. Now, there are different techniques of finding out the uncompensated demand function, which I will be picking up when I'll do duality part of the course. Right? But right now, I'm just giving you one example. Okay. So I'm picking up a very simple example. Guys, what is it that we have done just now? What is it that we have done? Okay, I'll just show you. So we had this budget constraint, and then I asked myself, given this budget, what is the maximum utility I can achieve? Is this the maximum utility? No, this is the maximum utility. So this approach is called utility maximization. Right? When you are maximizing utility subject to the budget. Let's look at the another way of looking at the same problem. You might ask yourself, I want to achieve this utility. Now, what is the minimum expenditure I have to make in order to achieve this utility? I can achieve this utility even by spending up this much. But is this the minimum one? No. This one is the minimum one. Right? At this point. So this approach is called expenditure minimization. Right? I'll be talking about this. I've just given you a very brief account of what duality is. So these are your dual problems. So like two sides of the same coin. Now, here, what is it that we have done? We have maximized the utility subject to the budget. Clear? Here, we will be minimizing expenditure subject to the utility. That's what we have done here. Clear? So we are now minimizing expenditure subject to the utility. So my expenditure function is this P1x plus P2y, and I want to achieve this given utility. This becomes my minimization problem. So I have to minimize this subject to this constraint. So my constraint is this. Okay? And supposedly if my utility function is just uxy equals to xy, this is my utility function. And if I'll set the utility, let's say at u bar, this is the utility, this is the number of utility which I'll have to achieve. So u bar minus xy. Then the technique is same. How many partial derivatives you need to find out? One for each variable and one for the constraint. So p1 minus lambda y, del L by del y, p2 minus lambda x, del L by del lambda is u bar minus u of xy. Here in this case, this is u bar minus xy equals to 0. That's the same thing. So again, you will divide first by second, and what you will be getting is p1 by p2 equals to y by x. So y equals to x p1 by p2. Clear? And now I'll substitute it back. I already have y equals to x p1 by p2. This I have. Now what I'll do? My utility function is u equals to x into y. So in place of y, I'll do what? I'll write x into p1 by p2. So u bar equals to x square p1 by p2. Clear? So I'll write everything in terms of x. So my x is now root of p2 by p1 u bar. As you guys could see, and I've already told you that compensated demand functions, they are the function of prices and utility. Uncompensated demand functions, they are the function of income and prices. So that's what you know. This is the function of prices and utility. Yeah, like this, right? So xh is p1 p2 u bar. So it is root of p2 by p1 u bar. And similarly, once you have solved for this thing, you can solve for y as well. So you can write your y as x is what? Root of p2 by p1 u bar into p1 by p2. Clear? So what you will have is basically your root of p1 by p2 u bar. This is what your y is. So y is also the function of p1, p2 and u bar. Right. So what is it that I have written out here? Nothing. Your Hickson demand functions or compensated demand function. I've already told you that these are called the compensated demand function, these xh and yh curves, and they are also called Hickson demand functions. Now there was one other question which was asked in 2011 paper, IES exam, question number 1a. It says that define compensated demand curve. We've already defined that. And how does it differ from the uncompensated demand curve? Even though it is not asking you to derive the compensated demand curve, and I've already told you one difference between them. That is, your uncompensated demand curve takes care of the total effect, which means both substitution effect and income effect, and the compensated demand curve only takes care of the substitution effect. Okay, we'll again look at this problem when we'll do the duality part of the syllabus, right?